Friends, last year I had set a question paper for paper number 4101 section A, the spectroscopic studies on inorganic compounds, and in the IR section I had set a question which was quite simple, but it was important because it utilized a number of principles to be applied. The question I was asking fundamentally about the symmetries which a complex can adopt under certain conditions, as well as the number of IR bands, whether they are allowed or not in Raman mode and IR mode. Further, whether a combination band also existed or not in the particular system that we had set. Now the system that we focused on was a trigonal bipyramidal molecule, a trigonal bipyramidal molecule FeCO whole 4 L. Now as you can see, this is a 5-coordinate system having 4 carbonyls and 1 ligand L. This molecule can adopt basically 2 structures. In the structure 1, we will have all the 3 COs in the equatorial plane of a triangle with the iron sitting at its center, and we will have in the axial sides the ligand L and 1 CO. So this is our structure 1. While in the structure 2, we will have equatorial plane, but now the ligand L will shift to the equatorial plane, while the axial plane will be occupied, the axial sides will be occupied by the carbonyl. So this is our structure 2. Now once we have these 2 structures, the question asked was, what symmetries can we assign to these 2 structures? Now let us focus on the first structure number 1. In the structure number 1, you can see that there will be a highest fold axis which will be along the axial direction, and this highest fold axis will be a C3 axis. If you recall, a C3 axis is basically an axis of rotation by 120 degrees. So you can see that if supposing you have a C3 axis along the axial direction, and if you do a rotation operation, you will be able to transfer each CO from one end to another end to the third end, so that there is a 120 degree rotation for all the 3 COs, and this will be fundamentally showing that this structure has a C3 axis of rotation. Besides this, it is also going to have planes of symmetry. So you will have a plane of symmetry which will be passing through one of the bonds, that is a bond between an iron and CO. So there will be 3 planes of symmetry, and these will be basically the vertical planes of symmetry. So you will have a C3 axis of rotation and vertical planes of symmetry. Thus, the point group which we can assign to this structure will be a C3V. Thus, the structure 1 adopts a C3V type of symmetry. If you look at the structure 2, here we cannot have a C3 axis. This C3 axis will not exist along the axial direction, because you do not have identical ligands in the equatorial plane. You have one L which is of different nature than the 2 carbonyls. So you cannot exchange, if you do a 120 degree rotation, you cannot exchange the ligand L with the ligand CO because they are of different nature. Hence, the C3 axis will not exist. What can exist is a C2 axis which is passing through the iron atom and the ligand L. So, the C2 axis, if you recall, is an axis of rotation by 180 degrees. Now, if you can see easily that if you perform a C2 rotation, then this CO in the axial positions will move by 180 degrees to the other carbonyls and vice versa. In the same manner, the two COs in the equatorial plane are also going to move from 180 degrees from one side to the other side. Thus, this shows that the highest fold axis in this structure 2 is the C2 axis. Besides the C2 axis, this is also going to have a vertical plane of symmetry, as well as it is going to have a molecular plane of symmetry. So basically this is going to have two vertical planes, and hence this is going to be assigned as a C2V symmetry. Thus we have the first part of the question that we have been able to solve is that there are two structures which can be adopted by a trigonal bipyramidal FeCO4L, and one of them is going to have a C3V symmetry, another is going to have a C2V symmetry. Now, in the second part of the question, it was asked what is the number of IR bands associated with each symmetry and whether they are IR and Raman allowed or not. Now, to be able to find out whether how many IR bands will exist with each symmetry, what we need to do is we need to write a tau vibrational, that is to say a reducible representation for vibrational mode. Now, for that particular purpose, you need to have a basis set. The basis set in that particular case will be chosen as the bonds, that is to say the iron CO bonds, because it is the bond stretch basically which is going to be important. And fundamentally the stretching mode associated with this particular case will represent the basis set. Hence, assuming the first thing is to assume the basis set as the bond of the carbonyls. Then what we need to do is, once we have this basis set, then we have to use the symmetry operations of this particular point group and see how the what happens to the COs and how their characters are changed or unchanged upon application of the symmetry operations of that particular point group. So let's focus on first of all structure 1. If you have the structure 1, in the structure 1 it is a C3V point group. In the C3V point group you have basically a identity operation, a C3 operation and a sigma V operation. Now if you use a identity operation on this, in this on the C3V, you can see that in the equatorial plane there are 3 COs and they will remain where their positions were. That means there is not going to be any change in their positions under the identity operation. Now if you remember the rule that if there is no change in the position of the ligand or the atom that is under consideration, then the character of that will be 1. Since there are 3 COs, therefore the character will be 3. So under identity operation, since there are 3 COs and they are not changing their positions, the character will be 3. If you look at C3, you find that all the 3 COs change into one another. That means COA goes to B, B goes to C, C goes to A, so on and so forth. This means that since all the COs are changing, therefore the character will be 0. If you look at sigma v, then since there will be 3 sigma v's and a sigma v will carry the iron atom as well as the CO, so that CO will not change its position. But what will happen is, supposing you are doing a reflection about this plane, let us say this is one of the planes, then what will happen is there will be a exchange reflection of CO, this CO and this CO. So there will be a reflection between these two COs, whereas this CO shall remain intact. Therefore the character under reflection operation will be 1. So these are the characters that we have been able to obtain under the reducible representation in the equatorial plane. In the same manner, we can write the reducible representation in the axial position. In the axial position, you can see that you have only one CO and another ligand is the L ligand. In this case, if you perform the identity operation, the CO remains where it is and therefore the character will be 1. If you perform the C3 rotation, the C3 axis is passing through the CO and the L axial line. Therefore, again there will be no change in the position of the CO because the CO will remain where it is. Hence again there will be a character of 1. If you take sigma V, the sigma V will carry again the C3 axis along with it. Therefore, the CO will not change in the axial position also. The character therefore will also be 1. These are therefore the characters that we have been able to locate under the C3V C3V point group using the operations E, C3 and sigma V. Now the point is that if we want to know how do we relate these reducible representations to the number of IR bands that are possible, and what we need to basically look at is that you have to reduce this reducible representation has to be broken down into its irreducible components, and those irreducible components will then be part and parcel of the IR bands that are possible. Now, if supposing for that particular purpose we need to have a character table for this particular group. Now, the character table for all the point groups will always be given as an appendix in the exam paper. So you can always look back at the character table. Now, if we can just write down the various under the point group C3V, what is the character table? We'll just note it down. We have the following, again this following operations, and we have the representations over here A1, A2 and E. A1, A2 are non-degenerate while E is a doubly degenerate representation, and the characters associated are 1, 1 and 1 for this. In this particular case 1, 1 minus 1 and 2 minus 1, 0. Now once we have this, we can break down the reducible representation in the tau equatorial using this table such that we can figure out what components can be added to make up the representation 3, 0 and 1. You can see that if we take a representation which will be basically in this particular case we have a A1. If you take a A1 and a E, that means if you combine a A1 and a E, you will find that this A1 and a E will come out to be 2 plus 1, 3, minus 1, 1 will be 0 and 0 plus 1 will be 1. This means that this tau equatorial will be broken down into A1 plus E. If you look at the tau axial, it doesn't need to be broken down, because this tau axial already has the characters 1, 1, 1, which belongs to A1, so this is basically A1. So the number of irreducible representations which are found for tau equatorial and tau axial are basically 2A1 plus E. Now these representations are fundamentally associated with the tau vibrational that we have considered, because we have considered the we are considering the CO as a bond vector, or as bond as a basis for stretching vibrations, and therefore these irreducible representations are in fact reflecting the number of IR bands that will be associated. So basically it is saying that there are 3 IR bands which are associated with the symmetry C3V. Now we need to find out whether these bands are IR or Raman allowed or not. Now for that particular purpose, we have to invoke what is called the selection rule. Now if you recall, the selection rule basically says that the tau vibrational that you have, that tau vibrational must have under its the components at least A1, and or if you do not have A1, if you have a component which can be which can transform as a unit vector x, y and z, then you can consider that IR band is allowed. Let me repeat this point. What we are saying is that if you have a IR band which is associated with a tau vibrational, and the tau vibrational must have or must transform as unit vectors x, y and z, if it does so, then we are assured that those components are allowed as IR bands. Now you can see that in the tau, in this tau vibrational, that means tau equatorial plus tau axial, you have 2 A1s and 1 E. So we need to know whether the A1s are transforming as x, y and z, and what is the transformation property of E. If they are transforming as x, y and z, then we know that all of them are allowed. Now to be able to ascertain whether they are transforming as unit vectors x, y and z, we need to look at the character table once again. And in the character table, you will find that there are other columns besides the characters. There are other columns which we need to look at, and these columns I'll just modify this and write it down again, the representations. So what you will find is that under A1 you find that the transformation properties of this A1 is basically transforming as Z, A2 is transforming as RZ, E is transforming as X, Y. And if you look at the squares, then this is transforming as Z squared and X squared plus Y squared, and this is transforming as X squared minus Y squared and XY, and also XZ and YZ. So in the character table you will have, besides the characters, you will also have how the irreducible representations are transforming in the form of unit vectors and the squares of the unit vectors. So you can see easily that this A1 is transforming as Z. Therefore, these A1s are therefore IR allowed. E is transforming as x and y. Again, they are part of the unit vector x, y and z. Therefore, the E is also IR allowed. So, all the three bands are IR allowed under the C3V symmetry. If you look at the squares, again, the squares are useful because the selection rule for the Raman mode says that if the irreducible representations transform as the squares of the unit vectors, then those Raman bands are allowed. So here you can see again A1 is allowed because it is a square of z, and as well as it is a sum of squares of x squared and y squared. So again Raman allowed, it's also Raman allowed. And E is transforming as a x squared minus y squared as well as xy, a combination of xy, or it is transforming as xz and yz, again a combination of x and z and y and z. Therefore, E is also Raman allowed. So which means that we have been able to solve the second part of the problem, wherein we have found out that one of the symmetries which is adopted by the trigonal bipyramidal FeCO4 is actually C3V, and under that C3V symmetry you have three IR allowed and three Raman allowed bands. Now let's stop here for a moment and take up the next symmetry, which is C2V.